All right, next I'd like to look at a problem in which we have to decompose vectors into components. And so this problem then is similar to this touching scene that we see where a father is lovingly spinning his son round and round in a circular path. And but I mean, even though this is kind of a cool picture, what we can do is to look at something like this. Okay? And this takes into account all of the basic physics of the problem without us really needing to add in a whole lot of details. And so what we would consider then the child to be is a point mass in which the location of the mass is what we call the center of gravity position of the child. Now for the moment, we're not going to worry too much about how to calculate center of gravity. We'll get to that later. But let's look at an equivalent problem in which we've got essentially a point mass that's going round and round in a circle like this. Okay. Now the circle does not have a center up here. The center of the circle is in a horizontal plane. Okay, so the center of the circle is down here. Okay, and so let's ask then for this problem, let me just draw this thing with, and I'm going to make this a 30-degree angle. Let's find the velocity such that a 1 meter string with a mass connected makes a 30-degree angle with the vertical. Okay, so here's our mass. This is our mg here. This is our tension in the string here, T. And let's set the length L of the string equal to 1 meter. And so what we're looking for then is the velocity so that the mass maintains a 30-degree angle to the vertical. And so what we first of all need to be aware of here is that this is the radius of the path, r. It's not L, not the 1 meter, but it's the r value here because the mass is going around and around in a horizontal circle, like that. Right? And so what we can say here then is that r is equal to L sine theta, or L sine 30. And so we'll want to hang on to that for later, but we don't just want to automatically accidentally put in that r is equal to L because it's going around in this horizontal circle. The other thing that we're going to need to do is decompose the tension vector into vertical and horizontal components. And so let me do that, a little bit bigger picture here on the right. And this is something I hope that you'll always try to do too, is draw big pictures. And don't try to squeeze all of your detail into some little tiny piece of the paper. Okay, and so if this angle here is 30 degrees, then that means that this angle here is going to be 60 degrees. And so we can break up the tension vector into horizontal and vertical components. This is going to be t times the cosine of 60. And this will be t times the sine of 60. And so the tension vector then is really busy in this problem. It's doing double duty. It's a multitasking force because the vertical component must support the wave, or T sine 60 minus mg equals 0. That gives us T sine 60 equals the wave. And so notice I'm measuring from the horizontal here rather than from the vertical angle. Okay. But in the x direction, so we've got a y direction here, but we've also got an x direction. And that x direction is positive inward toward the center of spin. Okay, and so we can then say the sum of the x forces, just like we've done in the previous problems, is mv squared over r. Okay, and so there's one x force, and that's just the x component of the tension, equals mv squared over r. Okay, so we can take this value for the tension if we want and plug it into that expression. The tension here is mg over sine 60. Okay, so if we write it this way, we've got mg over sine 60 times the cosine of 60 is equal to mv squared over r. Or this gives us mg times the cotangent of 60 is equal to mv squared over r. Okay, so now we're in a position where we can solve for the radius. We see the radius from this expression then is, you can cancel out the m's. And so v then is going to be the square root, again, the square root of rg times some other factor, in this case, the cotangent of 60 degrees. Okay. And that's also the tangent of 30. Okay, so I can write it that way too. I don't need to make that change here, but this is Rg tan 30. Okay, because the cotangent, the inverse of that is the tangent of the complement. So here's our 30, 60, 90 triangle. This is 1, 2, root 3. So the cotangent of 60 is equal to that's adjacent over opposite, so it's 1 over square root of 3. But the tangent of 30 is also opposite over adjacent, so that's 1 over square root of 3. So that is something that always works in trig. It's the tangent of an angle, the cotangent of the complement. That kind of works the same as the sine and cosine does. All right, so here then, just because I feel a little more comfortable working in terms of tangent functions, I'm going to leave it this way, and I'll make this the square root of rg times tangent of 30, which is 1 over root 3. Okay, so our velocity then, if we plug in those numbers, v will be equal to square root of r. Now, we don't want to just go, oh, it's 1. No, it's L over 2, L times the sine of 30. So that's 1/2 meter times g, which is 10 meters per second squared, times 1 over square root of 3. Right, so that gives us 5 divided by the square root of 3, square root, which is 1.7 meters per second. Okay, so this is our first example where we've needed to take a vector and decompose it into x and y components, where here the y component supports the weight, and the x component, the t cosine theta component, supplies the centripetal force. Then by just substituting one equation into the other, solving for t, plugging that in here, we get our final result. Now, although this result, that the velocity is equal to r square root of rg tangent 30, is the solution to this problem, what we're going to see is that we have a similar problem mathematically that doesn't seem like it would be similar at all. And that is the banked race car track problem. Oftentimes, what is done in order to not have to rely so much on friction is to figure out how much you would bank a track for a certain velocity that would be a typical velocity that race car drivers would be taking that on that track. And so for this problem, let's say that the angle is 30 degrees. And let's say that the radius of this circular track is 100 meters. And let's find the velocity that will allow for the race car driver to be able to take the circular track. So it's going round and round in a circle, but on a banked track. We just want to find the velocity so that the mass will stay on the track, where the theta angle here of the inclination of the track is 30 degrees. Okay, and so we're basically saying, well, we're stuck with a track that has this, and so we're going to see what kind of a velocity will result from that. All right, so what do we want to do here? Well, on this mass, we've got a normal force, and we've got a weight force. Now, if you'll recall, in our last example, what we had for the mass on a going around in a horizontal circle like this is we had a tension force and we had the weight force. So although it doesn't seem like this kind of a problem is similar to that one, we see that the force factors are pretty similar in the way that they behave mathematically. So if this is 30 degrees, that's 60 degrees. That's 60 degrees, then that makes this 60 degrees, but this is 90 degrees, and so that's 30 degrees too. Okay, and so just with a little bit, here's 30, 60, 90, 30, 60. But if this is 60, vertical angles are equal, so that's 60. But this whole angle here is 90, so that makes this angle also 30 degrees. And that's also the same as this angle, which we already knew was 30 degrees because vertical angles are equal. And so either way that you want to look at it, you get that that angle here is 30. And so now we can find the components of the normal force. This is going to be F normal cosine 30. This is going to be F normal sine 30. Okay, and so here it's the normal force that is having to do double duty. Remember here, it was the different components of the tension. One had to support the weight and one had to make the mass go in a circle. Here, this component supports the weight and this component makes it go in a circle. And so, even though we're on an inclined plane, we say, well, I thought you told me to make the coordinate system along the plane, not horizontal and vertical. The fact that we're doing a centripetal force problem. That trumps everything else that we were doing before with changing the coordinate system to be aligned with the incline, because we have to make the positive direction toward the center of spin. And also, we're not interested in the mass going up and down the plane because we want it to be balanced at that point. So there is no motion of the mass on the plane. And so that eliminates the advantage of using the plane as the coordinate system that's perpendicular and parallel to the plane. And so this is our chosen coordinate system then for all centripetal force problems. And then we could say that the sum of the y forces is equal to Fn cosine 30 minus mg. That's equal to 0. And then the sum of the x forces is going to be F normal sine 30 equals mv squared over r. And we can solve this for the normal force and plug into that equation. Or we can just, here if we write this as F normal sine 30 is mv squared over r, and we write this one as F normal cosine 30 equals mg, we can just divide the two equations. That cancels out the normal force. That gives us the tangent of 30 equals mv squared over r divided by mg. Or, once we cancel out the m's, this gives us v is equal to square root of rg tangent 30. And notice that's the exact same solution we had for the ball that was going round and round in a horizontal circle. So what we see then is the banked race car track problem without friction is mathematically identical to the pendulum going around in a horizontal circle. And so for this problem then we can, again, plug in and see what velocity we've selected for in this kind of a race car track. Square root of rg, well r is 100 meters times g, which is 10 meters per second squared, times the tangent of 30. So it won't be the same number that we got in this problem because the r value is so much different. But the angle of inclination of the incline is the same as the angle from the vertical. And so this gives us 100 over root 3, square root of that. Which is 7.68 meters per second. Okay, so that at that velocity, then you wouldn't need friction to hold you onto the incline. You would have selected for a velocity that's equal to 7.68 meters per second. Okay, now what I wanted to do next is look a little bit at, I'm not going to completely solve this problem. I'm going to let you do that. But in this next example, what I want to do is look at a banked race car track with friction. So let's make the angle of inclination 30 again. Make the radius r. Make that 100 meters if we want. And then let's ask now, what's the maximum speed that I can go on this circular track before the car starts to slip? Okay, now I'm going to set this up for you, but I'm not going to completely solve it because you have a little exercise in which you will be doing this and showing me how well you understand this material. All right, but let's look at it. Here we've got the forces that I was referring to before, mg and F normal. But now, because if we go too fast, this thing is going to tend to want to slide up the incline. We also have the static friction force, which is going to oppose that motion as the mass starts to slide up the incline. Okay, and so let's draw a little bigger picture of that over here, because I think that the vector diagram here is super important. Here's our normal force. Here's mg, and here's the static friction force, Fs. This angle, let's say, is still 30 degrees. Now we're going to be pushing the static friction force to its maximum. So we know that the static friction force here has to be equal to the coefficient of static friction times the normal force. Because we're looking for V max before the car starts to slip and slide off the track. All right, so now because our coordinate system has to be one that is vertical and has for y, and has the x component of all of the forces pointing toward the center of spin, we've got a little more significant kind of vector decomposition to do here. Okay, so what we did before was we said, well, mg, we don't have to break that up into horizontal and vertical along the incline, because we're choosing the coordinate system to be just horizontal and vertical. Okay, so that means that the normal force, again, has to be broken up into components. This is 30 degrees. That's F normal cosine 30. This is F normal sine 30. But now the static friction force, too, has to be broken up into x and y components, because that's also not aligned with our coordinate system either. Okay? So this is F static. So this is F static cosine 30, because this angle is also 30. These two lines are parallel and they're cut. So we have opposite interior angles are equal. And then we have, this is F static sine 30. Okay, so now we've got x and y components for the normal force and for the static friction force. Only mg in this problem did not need to be decomposed. So here then we can say that the sum of the y forces is equal to 0, or F normal cosine 30 minus F static sine 30 minus mg equals 0. That's the sum of our y forces. This force is positive. These two are negative, which is what I've got here. And then the sum of the x forces have to equal mv squared over r. And so the x forces then are going to be F static cosine 30 plus F normal times the sine of 30 equals mv squared over r. So this gives us a set of equations, two equations and two unknowns, with which we can solve first for the normal force, which you could probably get from the top equation, then plug that value in for the normal force to the bottom equation, using the constraining function that F static maximum is the coefficient of static friction times the normal force. Okay, so I'll leave it to you to finish this problem and to show me how well you can solve it.